Hi, good morning. What a pleasure to be here. I've been working in technology for almost 20 years, and probably like some of you who've also been working in technology for a while, you've realized that the pace of software has really changed over time. So cast your mind back to a very long time ago when you started. Perhaps you, like me, were sort of seeing releases every 8 months, right? And if you think about today's age of software, particularly with cloud and particularly with the sort of fast pace of startups, you can imagine what Amazons and Googles are constantly doing about releasing software all the time. And this is really the essence of thinking about how do you keep software systems supple, changeable, and this is really the point of what building evolutionary architectures is about. So I work for N26, and one of our missions is really to be the first bank you'll love. It's an interesting mission statement, because you often don't hear about the word bank and love in the same sentence. And we're really out to sort of change that. One of this is really about putting a lot of emphasis on user focus. So this is something that Sebastian talked about, where all of our development teams are very close to users as much as possible to really understand the problems that you as consumers have with banking services, and the goal of trying to make that as easy as possible. Now, I'm sort of chief scientist and also the former CTO, so I do a lot of sort of talking about what we actually do. And some of the sort of backgrounds of what I've been talking about are things like technical leadership, retrospective, so working in agile methods for a long time, and also the book on building evolutionary architectures, which you can sort of tweet me if you're interested in. I also run a course on technical leadership skills. And for those who are interested, I also run a newsletter called Level Up, which is really aimed at tech leaders who want to keep up to date in everything to do with leadership, technology, and everything about modern engineering organizations. But one of the interesting things about evolutionary architecture is we were particular to choose the word evolution. Now, it's kind of interesting when you think about the world of continuous architecture or agile architecture, but for us that didn't really suit what we were aiming for. Now, what's really interesting about evolution is something that perhaps that other people outside of technology can really understand. And one of this is really about the basis of change, right? So the interesting theory of evolution is that the world is constantly changing around us. And so one of the interesting points is understanding that you can't do anything to stop that change. If you don't like that change, it'll still happen. And one of the interesting things about evolution is if you're going to be successful as people running companies or building software for companies, you need to keep your software systems suitable for their environment as well. So Sebastian was talking about the speed of continuous delivery if you don't even want to do that. But if your competitors are building up their software so that they can release their sort of features faster and quicker, your company is going to be at a competitive disadvantage if you don't keep up to date. And so one of the theories or the sort of interesting questions that we explored with this book was really looking at this idea of understanding how change comes in different areas, right? So we're often sort of focused on this very technical area, right? So the frameworks, the languages, lots of different aspects that we've seen change over time. And even in the Java community, we see everything evolving in the sort of JVM as well, right? So you've seen Clojure come out, you've seen Scala, Kotlin more recently, and now we're also seeing a faster pace of the Java language itself. But these are only the tools of what we use, and we use these tools to produce useful software for users or end systems. And so the other aspect of change that we have to deal with is also the way in that software is being used or how it gets consumed. And this is really about the domain, right? So these are often about the business requirements or the wants from other parts of the business for us to drive the change that we want to have. So if you think about software, about sort of thinking about music, we used to buy CDs, right? We used to buy albums of CDs. Today you probably use something like Spotify, where it's a subscription service. But obviously that changes the nature of how we have to account for playback, licensing, and being able to account for that use as well. There's always new markets that are popping up and new competitors as well. And so that creates new demands for how we actually have to evolve our software. And so understanding that this change is inevitable, what does that mean for how we actually go about designing systems? And we sort of explored this question of, if change is inevitable, then what does that mean? So we asked the question is, what if we really architected a system that was designed for change? So as a first principle, how would that change the way that we build software? How would that change the way that we chose things of how we built that software and architected that? So a definition, we love definitions, and it's good to sort of start with this. We'll explore this throughout this keynote. An evolutionary architecture supports incremental, guided change as a first principle among multiple dimensions. And we'll look at all of these elements. So the first thing is really incremental, right? And in software, what we are actually talking about is architectures evolving incrementally through generations. And what does that mean? Well, if you think about this from a biological metaphor, incremental releases represent these generations. So you might actually start off with a software system that you had planned, but you don't really know how that may evolve over time. You might choose to go to the latest sort of Java version. You may choose to perhaps pick Kotlin. Perhaps you're forced to sort of implement a feature that you hadn't really planned for before, but you can't really predict how this is going to go. You can sort of retrospectively look at that. And if you think about this over time, what you might end up with is actually a significantly different system than what you thought you might have actually built. Now, what's interesting is that this is really constrained by how quickly you can actually create a new release of software. So is your pace of change 6 months like in the old days, or 12 months in the old days of software? Or is it on a daily basis, right? So if you can release software faster, if something goes wrong, you might be able to actually reverse that because it wasn't fit for that sort of environment, and you might be able to actually explore something else to test out and evolve a more suitable system architecture. And so generations for us in software is actually another term that was cycle time, right? So cycle time is the time taken to get a simple change into production. But it's quite important that you can do this both repeatably and reliably, right? So it's not just about hacking stuff, throwing it into production and testing it against users, but actually having confidence that when you make changes, those things are actually going to work for the end use case. Now, what's good about this is that this is things that we're very common and familiar with. And these are really the ideas behind continuous delivery. But the ideas and practices of continuous delivery aren't enough. You also need the organizational support to be able to do that, right? So even if you implement really wonderful build pipelines, really wonderful sort of automation, you also need to have things like the DevOps culture to really support you being able to both ship sort of those systems into production, but also to be able to monitor and to be able to actually respond to issues as well. So once again, it's not just done that we've built the system, but you also need to think about how that system is actually reacting in production and making sure that we bring that feedback into our sort of systems as well. So all of the sort of foundation practices from continuous delivery and DevOps are kind of your cornerstone for being able to build evolutionary architectures. And so here are some of the sort of key practices from each of these different areas that we believe are fundamental building blocks. If you're not doing any of these are the practices that you want to be investing in to make sure that you can actually start to think about building evolvable systems. So if we think about the process of architecture, we're often thinking about this idea of, what is the system that we're trying to build, architecting, and then we go about developing the system, and then we release this. But I think one of the first interesting questions that we should explore is, what is architecture? Naming is really hard, and we often don't really have a similar sort of understanding about what this is. So let's talk about what other people have talked about. So Martin Fowler talks about software architecture is the decisions which are both important and hard to change. Now that's kind of interesting, right? So what is important, and also, why is it hard to change? What happens if you make something that was an important decision easy to change? Stops becoming architecturally significant, and it's just as simple as reversing a design change. So it's not really a binary, but it's a bit more of a spectrum. Simon Brown talks about architecture is about understanding what you need to build, creating a vision for building it, and making appropriate design decisions. So do people have a consistent idea about what you're actually trying to evolve to, even though that may change over time? Or do people have different mental models about that as they're making design decisions? I like this one as well from Ralph Johnson. Architecture is the decisions that you wish you could get right early in a project, right? We all set out to do what we believe is a good thing, the right thing, But we make mistakes, right? We learn constantly. The landscape of where our software is going is constantly changing. And so a decision we made back in the past may no longer be appropriate for today's environment in which that software is living. And so one of the interesting things is actually looking at this process, but actually thinking, well, we think that we make important decisions when we try to architect. We often think once we make those important, hard decisions, the development side's actually the easy stuff. And releasing, well, that's somebody else's job, and that's how hard could that be? But I'm sure most of you realize this isn't the reality of how we build software, right? So as we architect, what we thought was important may not be important at all. We might actually discover a trait that is even more important that perhaps we misevaluated. Development is just hard, right? So we learn a lot about the problem space as we're building software. As we showcase things to users and to perhaps people who have requirements, they actually say, oh no, that's not what I really wanted. Here's what I want instead, right? So we're constantly learning as we're developing. And releasing software in a way that doesn't disrupt users, well, that's much harder than we've thought. And if you're trying to do this with lots and lots of users at scale, that problem becomes infinitely more complex as well. So we need to stop thinking about this process of architecting, developing, and releasing as a linear process. We actually need to start thinking about this from a feedback loop perspective, right? So what we think is important, we design for, we want to develop that, and we want to get that into users' hands quickly and possible. But we also want to understand, is it appropriate for what we're actually trying to build? Right? If we put a big bet on a vendor tool at the heart of our system, and we get that wrong, if we get that into users' hands very early, we can actually perhaps undo that before more users start compounding on that, and migration becomes a problem. So we need to understand, as we ship software in real use, getting real feedback from production, how do we feed that information back into how we want to build our software? What do we want to amplify? What do we want to dampen? And the key to this is really understanding what your feedback loop is, and also trying to really make it smaller and tighter. So the key to this, your constraint to be able to get feedback about your architecture, is really your cycle time. So there's a really interesting book, if you haven't read it, it's called Accelerate. It kind of comes from the State of DevOps report. And in that book, Nicole Forsgren talks about metrics that allow you to measure this. And one of them is cycle time, so the time it takes to get change into production. Because if this is taking you 3 months to get change into production, that's a lot of time before you get feedback about whether or not you made the right decisions in production, right? So big bets, and what you're trying to do is create smaller bets as you go. So we've looked at incremental as the first part of this definition. So basis, practices of continuous delivery, practices of DevOps culture, making sure that you can get your sort of software into production. The second part of this definition we want to talk about is guided. And so what we talk about is evolutionary architectures are guided with fitness functions, right? So this is the where do we want to sort of optimize our decisions for, what type of system are we building? Now, fitness functions are sort of kind of well known in sort of the machine learning AI space. And a fitness function is basically an objective function that measures how close a given solution fits to a particular goal. Right? So when people are building sort of machine learning algorithms, what they're not trying to say is how you go about coming up with a solution. They just want to describe what does good look like. And this is kind of similar applied to architecture. So the question is, for the systems that you're building, what does good look like, right? How do you know that as developers are constantly making decisions, do they know what does a good decision look like according to that system? Now, in my experience, the pace of software is moving so quickly that a lot of people don't step back to think about, well, what is a good architecture for the type of system that we're actually building? And this is where we encourage you to think about the fitness functions that you're defining for the system. Now, it's quite simple because a lot of these kind of elements are really thinking about what are the important characteristics and what are those things that are not so important for the type of system that you're optimizing for. These things are sometimes called non-functional requirements or cross-functional because they cut across the system, or sometimes your system quality attributes. And it's kind of an aspect that I'm sort of disappointed that we as an industry don't talk more about. So for the systems that we're developing, what are these characteristics that we really care about that aren't necessarily functional characteristics, but are system quality characteristics that we're trying to optimize for? And it's quite simple when you sort of list these out and you describe them with your team about trying to understand what type of system that, what are the characteristics that are important for this type of system. And so what's really interesting is that even within a large sort of company, you'll have different types of systems optimized for different types of characteristics, right? So for us as a bank, one of our core systems around payment transaction processing, we're really caring about low latency. We want only sort of immutability, so we don't want to have to reverse. We want to make sure that things don't get double booked. Those things are really key to our sort of system. But if we talk about some back office process, which is a sort of manual process, we don't really care so much about perhaps uptime for a system like that, because we care about it being sort of available during work hours, but not necessarily when people aren't there. So even within the same context, you need to optimize systems quite differently, depending on the system that you have, but you need to sit down and actually define what each of these are and what you're actually optimizing them for. Now, there are other sort of functions that you can sort of explore, and I want to give you two sort of examples. And you can often do these things through metrics, tests, and processes as well. So in the book, we describe many types of fitness functions. In this, I'll talk about two specific ones. So we'll talk about an atomic fitness function that is testing a characteristic. So in a lot of places, one of the things that you want to have in good code is good modularity, right? Good dependencies. And if you've used something like JDepend, a simple test like this can actually prevent sort of cyclic dependencies. So we know that changes are hard if one module calls another module only for it to call back, because you have then this weird inherent coupling, which is hard to change. And so you want good modularity, but if you just simply say that, then people don't get feedback as they're making code changes, right? And so this is actually a really good way of automating feedback as a fitness function. You stick that into your sort of continuous integration build to give continuous feedback. Now, if you're trying to expand this even further and you've got a sort of layered architecture, you can be even more specific with this. So you can actually expand this to talk about what type of layers and what is the relationship between these dependencies. And before something like Java 9 and modules, this is a way that you could actually enforce this as well. So in this case, you have a web depending on a utility package, a repository depending on a utility package, and the web depending on the repository. And if you get any other dependencies, this test will automatically fail. So it's an interesting way of automating the feedback about what is objective criteria about the type of system that you're building, and it's available to everyone on your team as they're constantly changing that system, right? So you don't need to be the sort of person that comes around and monitoring exactly everyone's code. You have automation to help you focus and give that feedback to everyone evolving that system. Now, another type of fitness function that we talk about is something that is continuous. So continuous you can think about as something that's always running, right? Something that's always checking to make sure the state of the system is alive. And the best example of this that we like to share is one about sort of the chaos monkeys at Netflix. So one of the interesting things about Netflix is that they really have optimized their systems for global-wide sort of reliability, and they have such a complex architecture that they can't really guarantee resilience. But one of the ways that they try to do this is by constantly trying to break parts of it. And they developed a whole toolkit of what they call the simian army, or individual monkeys, that are trying to break things, right? So you have things that slow down the network, things that randomly drop connections. And what it's trying to do is really break your sort of application. And like in sort of nature, as your immune system gets attacked, as you recover from like an incident, your immune system gets stronger. And this is kind of the evolutionary approach to really testing for resilience. And it's constantly running in production for Netflix. Now, funny story with Netflix, I think you all remember perhaps the S3 outage from Amazon. And this is probably one of the best examples where even Amazon suffered from images missing from some of their shopping sites. Netflix continued on because it invested in building this fitness function of continuously testing this art of resilience of being able to roll over to different availability zones. So think about what objective criteria you can actually build. And one of the lovely sayings from continuous delivery is if it hurts, do it more often. Not because we like pain, right? We shouldn't be avoiding, the pain, but actually we should be responding to that feedback, right? So we shouldn't defer that feedback saying, oh, we don't like that because it's hard. Actually, we have to get cleverer at responding to that feedback and finding ways to sort of think about how to fix those information and that feedback. So we've looked at incremental, we've looked at guided. Let's talk about some of these multiple dimensions that I'm talking about. So let's have a look at what types of changes that you might need to cope with. And some of them are the technical ones, right? So some of them are things like you need to add a new library, you might need to upgrade a new library, perhaps you're changing your platform, you have to migrate things. Perhaps you're trying to get rid of a library because you've now sort of moved on to a different type of library as well, right? So we're constantly making these changes to our systems just to keep up to date with that ecosystem, right? Security vulnerabilities are being found all the time. Just keeping our sort of software working as is with all the dependencies is quite a challenge by itself. But they're not the only changes that we have to respond with. We also have to respond to domain changes, or the things that drive our business and those changes, right? So it might be about new features that you're trying to release. It might be actually about expanding into a new product area that your system was never really designed for. Perhaps you're now targeting a different type of customer. These are all things that we can't predict, but we know that there'll be some sort of change over time. So let's have a look at a couple of architectural approaches and see how well they fit each of these different elements of technical change. So we'll look at a couple of different architectures. We may not explore all of them. In the book, we explore all of them. But let's first talk about the big ball of mud, right? So this is an interesting visualization. It actually comes from a dependency chart. And what we have here is a system of all the classes in the sort of system that we have. On the boundary of the circle, oh, sorry. I think my it's dying. On the boundary of the circle are all the classes, and then a line is basically a call out from one class to another class. And so what you would actually expect from a well-modularized sort of code base is clusters, where you can sort of see arcs of lines calling each other, and then maybe one small arc out as you have a dependency cross different modularization. But as you can tell here, one of the interesting things is you just see a whole network of different lines, which makes change really hard. And perhaps you've worked in a system like this, right? So let's say that you have to upgrade a logging library. Where do you go in the code base? It's like, oh, I have to go to every line of the code to see what might be affected by this. Let's say you have to go to a pricing change. It's like you have to analyze every part of where pricing might be used and scan through the entire code base. It's not clear about where that concept is actually located, and so you have to actually change quite a lot, or potentially look through a lot of code in order to understand some change. Layered architectures are probably a pattern that you're all familiar with. These are things that Spring MVC or Spring Boot or Ruby on Rails really encourages. So you can think about layered, perhaps your 3-tier layer. In this case, it's a little bit longer, but what we try to do is be very clear about what each layer is responsible for, right? So our presentation layer is very much focused on sort of formatting output for sort of the presentation tier. We might have a business layer, which is really sort of rules for perhaps aggregating different types of business rules or semantics. We have service might be about coordination and notification of different types of events. And then we have the lovely persistence tier, where we're actually trying to save things perhaps to the database, right? So let's say that we need to upgrade our sort of persistence API or library. Where do we go? Well, that's pretty clear, right? We just go to the persistence layer, and then we know that all of the sort of classes within this sort of module or package are the things that could potentially change. So we have less code to potentially scan through. But what happens if we actually need to make a sort of a business change, right? Then we actually have to think about, okay, which screen might it affect if we have to persist a new field? What are the rules associated with that? And then where do we actually map that to a database? So we actually have to cross all the different tiers as well. So a layered architecture helps us with the technical evolution, perhaps, but it doesn't really necessarily help us co-locate the sort of business changes as well. Now, what's interesting is that there's an interesting trade-off as well, because some of you might enforce extreme strict consistency. So whenever you have a new field, you have to make sure that there's something that gets copied from a presentation object to a service object to a persistence object. But some of you might trade that off for inconsistency and say, okay, since there's no business change, we're just adding code in just to copy from one sort of object to another, so maybe we can skip that. And this is an explicit trade-off that you need to make with your teams about if you prefer consistency and have extra code, or prefer less inconsistency, so maybe not as obvious to people, but less code as a result. And in this case, there's no sort of simple answer. It's more a team agreement from that perspective. Now, a microkernel architecture is sort of typified by something like Maven or Eclipse or Firefox, right? So this is basically your plug-in architecture. What you have is basically your core system designed to sort of serve its core need, and then you are allowed sort of extension points around that. Now, what's interesting about this is if you think about sort of technical capabilities, so let's say you need to extend Maven with a new type of tool, right? You know that you can write a plugin, but what happens if you want to tack it onto a part of the workflow early on in Maven, right? If you've worked on very complex build systems, this is where you sometimes find the weird limits of Maven, because that is built into the core system, which you can't actually change, right? So you end up with funny workarounds like extra profiles, you know, piggybacking on a lifecycle object that it was never really designed to do. And so here you're making actually a big bet that your core system is mapping to your core domain. Now, you can sort of see this a lot if you've ever looked at a tool that's been built on the Eclipse framework. You probably know that it's been built on the Eclipse framework because it looks still like Eclipse, right? It was never designed to perhaps look like a normal tool for other people. And so with the microkernel architecture, you can extend it to a certain point with some technical sort of extensions, but when it comes to the business extension, you're making a very big bet that it matches the domain that you have. So you have to be very careful about what type of system that you're building. Now, the architecture du jour, or the microservices, and I talk about microservices well-designed, where you have services per domain. Now, what's interesting here is that if you think about technical changes, so let's say that we need to upgrade a database about customers. We want to understand the relationship between customers with a graph database. Then we know that we can just go to the customer service and go, OK, well, this is the sort of service that has all those relationships. Let's now install a graph database alongside. So we can actually incrementally update that without affecting the entire set of services. And so here, we're actually introducing weird inconsistency across the macro architecture, but we can incrementally upgrade part of our system in order to respond to sort of new business need. And so what's interesting with microservices is that it allows us to do this incremental change over time at the trade-off that we'll end up with probably greater inconsistency across the macro architecture. And so one of the challenges that you have with implementing this type of architecture is if you have a single team maintaining all of those services, it can be a lot of extra cognitive overload to maintain all the differences. But if you actually have teams dedicated to different product areas, then actually that can actually work because there's less cognitive overload, and you can incrementally update technical and business changes as well, which is one of the reasons we see a lot of adoption for this. So we've looked at incremental, guided, and multiple dimensions as part of this definition. Let's quickly talk about a couple of practices. And we only cover 3 because we're running out of time. So one of them is really understanding Conway's law, and what we call is the relationship between the org design and the architecture. So in a lot of traditional, sort of older sort of ways of managing IT, you might think about having functional grouping, right? A team of user interface people, a team of back-end or server-side people, and a team of database experts. But often what you have is you have people that have communication difficulties across those different functional areas. And so you get a sort of tighter sort of cohesion across one layer, but then it's kind of decoupled from the next, so you get an interesting layering response. If that's the architecture you're wanting, then maybe that's the good sort of approach. But if you're looking for microservices, what you might want to think about doing is actually co-locating people to actually be fully functional around those areas. So the communication patterns of the teams will reflect themselves in the architecture. And depending on which architecture style you're aiming for, you should be conscious of this interrelationship. So make sure that you also have a say in how teams are organized and how they communicate, because they will inevitably sort themselves out in the architecture. And this is what we call about using Conway's maneuver as the inverse Conway maneuver, right? So design the architecture of your organization to reflect the architecture that you desire. A second practice is really focusing on principles. Engineers are making decisions all the time. How do you know what's reversible? You can't go and make every decision for every engineer out there, because that's too many decisions that you'd have to take care of. So what you actually want to do is define what are good principles to make decisions for. And if you've not developed any sort of architectural principles or design decision principles for your organization, you probably need to talk about what that looks like, rather than trying to enforce specific rules, which will always break down in particular exceptions. The third one is really thinking about how do you defer choices so you can change things out. right? So if you're dealing with externalities, what you really want to do is make sure that you have something like the adapter interface to really push that externality to the boundary of your system. Applied multiple times, and you might actually end up having multiple parts of your code calling this. And so that you often refactor that into a single point. And when you apply this to many parts of your system, what you end up with is actually the sort of hexagonal or ports and adapters pattern, where you have all external sort of interfaces on the outside of your system, and then you adapters to each of those external systems, so you can swap it out when you need to evolve that external dependency. You never know when, you never know if, but if you can, then it's isolated to a single point of your sort of system. So we've looked at lots of different sort of practices about technical and domain. There's a lot more to sort of cover, but I want to sort of close off by understanding how you use evolutionary architectures. So it's not something that you should use all the time, right? When we're thinking about new problems, we're often thinking about the choice between building or buying these things. In reality, it's a bit of a spectrum around that. And often when we're evaluating, we're often thinking about what does this thing give us, right? So if it's custom code, we have to write a lot of it in order to actually make something functional. But if we buy something off the shelf, so components off the shelf or software products, we get a lot of different things. You should also look at it through a different sort of lens of really understanding how easy is it to change, right? So if you're dealing with a product vendor, convincing them to change may be really hard, and also convincing them to make the changes at the pace that you need may be even more hard or very expensive for your company. So you need to look at it from that sort of change. And so when you're thinking about these, you need to think about the type of system that you're building, how much value it's generating, and how much change does it need to have. Right? So commodity software like email, you probably shouldn't be building this if it's not your core business. For things that aren't really value generating, but you probably need to make some adaptations to, so support, so tickets, right? You probably need to have a specific workflow, but it's not really strategic to your business. There are things that are experimental, so things that are maybe you write once, and if you don't find that there's a lot of attention, startups are a really good example, you want to throw it away. But when you have a system which is your strategic, so the core moneymaker for your business, your differentiator, you don't know how it's going to evolve, you don't know how it's going to change, these are the systems that you really want to implement evolutionary architecture principles on. So in conclusion, I'd like you to remember that the definition of evolutionary architecture is an incremental guided change thought about as first principles among these multiple dimensions. And most importantly, it's not just about software architecture, but it's about also the decision-making process of how you make these choices, and also the organizational and cultural elements to this. If you have any questions, please feel free to direct message me or tweet me, and I'll answer them afterwards. Otherwise, enjoy the rest of the conference, and thank you very much.